Hi guys, in this video I want to talk to you about another of Kirchoff's laws. It's called the Junction rule, and to sort of motivate it, I've sketched out this simple circuit right here. These are two bulbs in series. I use the term in series because they're one after another and they're on the same path. There's no split. So what I want you to think about is what is the relationship between I total. I'm going to call I total the current coming out of the battery. How does that relate to I1? And how does that relate to I2? Take a minute to think about it. I can actually go back into my FET simulation and measure this. In real life, if we set up the circuit, we'd have to use an ammeter. It's getting attached. And break up the circuit and insert this properly, but we don't got to worry about that because this is the digital world, and in the digital world we have this magic ammeter that can see through wires. And so when I hover over it, I see that the current coming out of the battery is 0.45 amps, and the current going through the light bulb is also 0.45 amps. So I1 is 0.45, and look at that. I2 is also 0.45. And in fact, what you should be visualizing is the charges moving through are the same throughout. So as an equation, I didn't write this out, but as an equation, I total is actually equal to I1 and is equal to I2. That's the equation that would describe this. That's the junction rule applied here. There's no splits, so the current throughout is the same. And you can think about it, if there's like 10 electrons coming out of the battery, those electrons don't get used up, right? So if 10 electrons come out of the battery, they're going to pass through light bulb 1, and they're also going to pass through light bulb 2. So that's the case here. That's why the current is the same throughout. What about for two bulbs in parallel? How is I total coming out of the battery again? How does that relate to I1 and I2, where I1 is the current through this lamp and I2 is the current through this lamp? Take a second to predict what's the relationship there. So we can actually, fake measure this. The current through, well, actually, let's go like this. The current through the resistor 2 is 0.86. Oh, that's interesting. The current through this resistor is about 0.87. And the current coming out of the battery, 0.86, 0.87. It's not 0.86, it's different. Do you see the relationship here? 0.87, 0.86, and 1.73. Yeah, quick math. Those two numbers add up together to be the total. And that makes sense because if I'm visualizing what the charges are doing, again, imagining positive charges. So if positive charges are coming out of the battery, let's say 10 coulombs of charge. It's splitting right now. And if 5 are going here, then I know that 5 are going there. So the equation that relates these two right now is I total is equal to I1 plus I2. I know that it's going into this, what I'm going to call it a junction, this intersection of wires, and it's splitting. And basically the charges leaving the junction add up to be equal to the charges going into that junction. That's Kirchhoff's junction rule. In summary, if the wire doesn't split anywhere like we saw in the series case, when it's just one after another on the same loop, then the current throughout is the same. But if there is a split, then the current going into the junction is equal to the sum of the current going out of the junction. We call it the junction rule, and it's really just a way of saying that the total charge is conserved. If I have, again, 10 electrons coming in, 5 going this way, then I know that there's 5 going that way. So that's Kirchhoff's junction rule. Hope that was helpful. Take care. Alt Shift